two things we want to do in this section. We want to be able to, given an equation, can we write the equation of the tangent plane, and then can we also find the normal lines, symmetric lines to the normal line. What normal are we talking about? We're talking about this. Remember in the previous section we said that the gradient is normal here to the tangent plane. So one thing we want to do is first find the equation of the tangent plane. Here, this perpendicular that's shooting from some fixed point, I want to be able to find the so-called equation that represents that tangent plane. That tangent plane is this plane that you see here. And then after that, our goal is to find all of the so-called symmetric lines to this normal curve here, or this normal line, excuse me. So any line that is said to be thusly after that parallel to this this perpendicular, that's what you want to find. And particularly, let's see if I can go back. We want to find symmetric lines to this particular tangent plane. So we're looking for these guys. Where's that? Now I'm just picking with the edges, but it could be any point in the tangent plane that's perpendicular. So we can find all of those. The neat thing is that if you want to try to move this surface diagram somewhere else, we can do it based on the so-called tangent plane equations and the symmetric lines to that normal line, or the symmetric equations to the normal line. Well, here, the definition of the so-called tangent plane and then the normal line, we take the definitions and we try to build the theorem by which we can have a formula to solve for such equations. One, the equation of the tangent line we're after, and then secondly, we're after the so-called symmetric equations to the normal line. Let f be differentiable at some fixed point on the surface S, and so this is given by here f of x, y, z is equal to 0. That is actually coming from, again, z is equal to f of x, y. And so we let capital F of x, y, z equal to f of x, y minus z. So we get this big capital F. We want to make sure that the gradient is not equal to 0. If the gradient is not equal to 0, then you can find its perpendicular. That's the goal. So here the plane P, the plane through P that is normal to the gradient is called the tangent plane. Talking about this tangent plane here. And this tangent plane is normal or perpendicular, right, to the gradient. The line through P having the direction of this so-called gradient is called the normal line to S. So this line through P, here P is right there at the center. They're talking about this line here. To find symmetric lines to this, we need a formula to be able to get all of these guys. Right? These guys are said to be symmetric here to the so-called normal line or the perpendicular. Well, let's see if we can build that. To establish the equation for the tangent plane let's say V is equal to x minus x naught I plus y minus y naught j plus z minus z naught k be a line in the tangent plane. To see that, P, which consists of the coordinates x naught, y naught, z naught, is fixed. On the surface of S. And if we take some other point, let's say Q, which has coordinates x, y, and z, be any point or any arbitrary point also in the tangent plane. By the definition, the gradient of f is non-zero so here by the definition this gradient is not equal to 0. If that be the case, then we have a neat property that this gradient is perpendicular to any line in its tangent plane. Okay? This needs to be a comma. It's perpendicular thus the gradient of f of x, y, z, the dot product of that with this point V is equal to 0. You recall from Calculus 2 that that was a property of perpendicular lines, that their dot product is 0. So we have that neat property that if you have two perpendicular vectors, one vector is perpendicular to the other vector, then their dot product is 0. So this implies then, now this gradient, you recall, is looking like this. This is the partial of f. Here we establish this at the particular point, the fixed point x naught, y naught, z naught, comma, the partial of f with respect to y at the fixed point, comma, the partial of f with respect to z at the fixed point. Here, dot product with x minus x naught, y minus y naught, comma, z minus z naught. This is equal to 0. So when I do that dot product, what I have then is capital F sub x at the point x naught, y naught, z naught times x minus x naught plus capital F sub y at x naught, y naught, z naught times y minus y naught plus capital F sub z at the point x naught, y naught, z naught times z minus z naught is equal to 0. This, my friends, is the equation of the tangent plane. Equation 1 is called the equation of the tangent plane. Now, what I'd better do is to give you the equation for the symmetric equations of the normal line, because the problems that we have in this section, they ask is one problem, but they ask two questions. From this equation, can you find one, the equation of the tangent plane, and then they also ask, can you find the symmetric equations of the normal line? So let me show you how we establish and find the symmetric equations of the normal line. What they do for that argument is, you see how V comes from the tangent plane? Let me go back and show you the graphic. What we've just found was we've just found the equation of this tangent plane. That's that equation. And here was the argument. The argument was this. The argument was, I have this fixed point here. That's the x naught, y naught, z naught. And then take any point in the plane, right? Some x, y, z. And you found the equation that represents that particular line. You change You change up the values of x, y, and z, or change the fixed point, and you get definitely a different equation. The question was, see, v is actually this line segment, right? So v is sitting in here. Then we're going to find the symmetric equations to the normal line. What does that mean? We're going to find all the equations that represent these guys. Now, to do that, we put a twist on v. That here, we say that now, let's take v to be in the so-called normal plane. Let's take v to be a point up here in space, right above the tangent. And then we establish those equations. And when I get through writing both equations, then I'm going to show you in something that you can go back to algebra and kind of make the connection to see why the equations are different, but they have some similarities too. Very neat property. I'll show you that in just a moment. I think I better use a different page. So now, we establish the symmetric equations to the normal line. So here we take v, just x minus x naught, comma, y minus y naught, comma, z minus z naught to be a point in the normal space of the gradient. So that's that little twist on v. Basically x naught, y naught, z naught still is fixed at p, but now v is coming from out in the space. So instead of q for the tangent plane, instead of picking q in this tangent, see if I can draw that. Instead of picking q here, we pick q now to be up here because I want to find equations that are parallel to this normal vector. So here's how we do that argument, is this. We say that here, this vector v, we want to establish the idea that v is parallel to that normal, to that gradient of f. So here, we take V to have the property with the gradient of F that V is parallel to this gradient. Now again, for two vectors now to be parallel, they differ by a scalar multiple. For two vectors to be parallel, they differ by a scalar multiple. Okay? So recall two vectors are parallel if they differ by a scalar multiple. In other words, if I have one line or one slope, I can find the next slope by just taking a number and just multiplying it to that guy. Right? So they differ by a scalar multiple. So let T be the scalar with T times the gradient of F at this point x naught, y naught, z naught is equal to V. Now from there we can establish the equation that we need in terms of these symmetric equations. Let's see. This is T times, that gradient is F sub x at x naught, y naught, z naught, comma, F sub y at x naught, y naught, z naught, comma, F sub z at x naught, y naught, z naught. That's equal to here x minus x naught, comma, y minus y naught, comma, z minus z naught. Now if you simplify this, this is T times this partial derivative at the point that's equal to x minus x naught. Then secondly, this is T times the partial of F with respect to y at the point is equal to y minus y naught. Do you see how I'm getting that? If you have one vector equal to another vector, then their corresponding parts are equal. Right? This is T times the partial of F, so just multiplying the T times this term here, and it's set to equal, like that first term, they're equal. This is equal to this term over here, times the T, obviously. And then this part is equal to its part over there, times the T on the left side. Now, if I take these three equations, and if I divide each one by its partial derivative, I have this. I have T is equal to, let me write that downstairs. I have T is equal to x minus x naught all over the partial of F with respect to x at the point x naught, y naught, z naught. That's for the first one. It's divided this equation here by this partial of F with respect to x. Do the same thing for the next two equations. So I get here t is equal to y minus y naught divided by its partial derivative. Then t is equal to z minus z naught divided by its partial of f with respect to z at x naught, y naught, z naught. Now notice that all three equal to t, right? So that means that I can set all three equal to each other and you get symmetric equations. That's the idea. So here, x minus x naught over, and if it's okay if I can just, well, I was going to just write that the shorthand, but I'll write it out. The partial of f with respect to x at x naught, y naught, z naught is equal to y minus y naught over f sub y at x naught, y naught, z naught is equal to z minus z naught over f sub z at x naught, y naught, z naught. We call these the symmetric equations to the normal line. All right. Now, you see these equations, these symmetric equations, and then when we go back and you look at the equation for the tangent plane, for both of them, if you look at these, the difference is where you place those partial derivatives. Right? For this one, the partial derivatives are in your denominator. And then for the other, it's the vector v times those partial derivatives. Now, you recall from this algebra, pre-algebra, that for two lines to be perpendicular, their slopes differ by what? Negative reciprocals, right? So you see the reciprocal part, and if you work these equations together, you will see the negative if you work it out. So you have that property happening. So that's why you have, for one equation, the slope is times, and for the next equation, the slope is downstairs, right? So you see that reciprocation, and you do get that negation. Where does the negative go? The neat thing about that parameter t, it seemed like the t just went away. It's contained within the t. That t could be any real number, negative or positive, and so you get that negation if you want to actually look at how the slopes interchange with being negative reciprocals. So now with that said, let's look at a problem. Here they give us one equation. Part A, you want to find the equation of the tangent plane to the surface at the given point, and then part B, find a set of symmetric equations for the normal line to the surface at the given point. So you notice from both of how we built those formulas, how we built the equation for the tangent plane, how we built the symmetric equations for the normal line, that they both involve the gradient. So let's find those partial derivatives. So here we're going to find, need to capitalize that. So f sub x is 2x f sub y is 4y, and then f sub z is 2z. So this whole talk about x naught, y naught, and z naught is really at this point here. So the partial of f with respect to x at 1, -1, 2 is equal to 2 times 1. That's just 2. The partial of f with respect to y at the point 1, -1, and 2 is equal to 4 times -1. We get -4. Then the partial of f with respect to z at the point 1, -1, and 2 is equal to 2 times 2. We get 4. So for part A, that equation, remember, it's the partial derivative times the point v, which is x minus 1. Then this is plus, or here, but this is -4, so just put the -4 there, times y minus a -2, that's y minus a -1, that's y plus 1, and then plus this 4 for this partial of z, of f with respect to z, times z minus 2, that's equal to 0. And we simplify that to find the equation of a plane. This is 2x minus 2 minus 4y minus 4 plus 4z minus 8 is equal to 0. We get the variable terms on the left side, get the number by itself on the right side, and you have the equation of a plane. 2x minus 4y plus 4z, that's equal to, we get, this is -10, -14, we get positive 14. So that's the equation of the tangent plane. Now part B is always easy. Once you get this line right here, you look at that and you get part B. So part B is just x minus 1 over 2. That's equal to y plus 1 over -4. That's equal to z minus 2 over its slope, its tangent, over 4. That's it. So working the problems in this section is a whole lot easier. Yeah. The first one is called the equation of the tangent plane, and the next one is called the symmetric equations for the normal line. Yes, sir. Okay. Everybody got that? All right, let me give you one now. What is capital F? Because you'll need capital F in order to get the right partial derivatives. What is capital F? neat gas station by the house in Texaco. Those guys, they get that coffee from down south and from Colombia and different places, and they bring it up here, and they have the beans and everything, man. They roast. They have a big roaster where they're roasted, and you can just buy the beans yourself. And man, I tell you, this is some strong stuff, man. I normally don't. They have some coffee from Ethiopia. They have that there as well. And I'm really not a regular coffee drinker, but I had a cup yesterday morning, regular coffee. I normally drink decaf, and so about a month or two ago, I was drinking regular coffee. Just strange for me to drink regular coffee, and it started making like my head kind of spin a little bit. And then at nighttime, before I went to bed, I felt strange. So, well, I'm used to decaf coffee. That's what my body was, So I guess this caffeine is just not so good for me. But anyway, let's see for part A. Let's see if you got this. For the equation of the tangent plane, that you get 6x minus 4y minus z equal to 5. Got that? 1, 2, 3. Okay. 1, 2, 3, 4. All right. And like I said, 50%. You don't believe me, man. I told you I'm a prophet. Oh, no. And then part B, I'll work it out. I definitely want to show you. X minus 3 over 6 is equal to y minus 2 over negative 4 is equal to z minus 5 over negative 1. Sir? Huh? Oh, okay. You had your negatives backwards. Yeah. That meant that it wasn't right. I'm going to show you. It's the question of how do you find capital F? Is F z minus little f of xy, or is capital F little f of xy minus z? If you had it flipped, then your signs are different. Now, I told you in the beginning when we first established this, let me back up, because I'm like Miss Summers, and she was our 11th grade teacher, 11th grade math teacher. She would say, y'all don't believe me. Miss Summers, you don't believe me. So look, let me show you, because you don't believe me. I know. I went down to Selma about maybe it was about 14 years ago to preach at Second Baptist in Selma. And she's not a member there, but she heard on the radio that I was going to be our church coming down there, and she came over to hear me. Well, I will say this. I probably flunked as a preacher, and I felt bad about that. I didn't do the best that I could have done. But Miss Summers was there, so I was happy to see her. She was looking good. Yeah, she was a trip, man. Her glasses were always broken. One side was always fixed, and the other part over here, the other handle was just missing. And she'd say, let me find my glasses. And her glasses be all like that on her face and stuff, man. She was a trip. And but we all knew that she carried a pistol in her purse, and so nobody messed with Miss Summers. And so well, they had some big football guy kind of got loud with her, and the rumor was that she said, let me find my purse. Let me find my purse. So, oh, boy. You got to love South Alabama, man. Back in the 70s and the 80s, it was good times, I tell you. Oh, boy. Now, let me find it. I think it was right at the beginning. Z is equal to f of xy. That's what this problem you just got through doing looked like, right? Z is equal to some x's and y's. Let capital F equal little f of xy minus z. Just basically just minus z from whatever you have with the x's and y's. That's capital F. If you have it the reverse, then you have your z would have been positive for your slope. So just make sure you get that right. So you come here, and so you have to say that capital F of xyz is equal to x squared minus y squared minus z. And then you get what you want. If you have it the reverse, you have positive value for z. So the partial of f with respect to x is 2x. The partial of f with respect to y is negative 2y. The partial of f with respect to z is negative 1. If you had it the other way, you would get positive 1 for f sub z. From how capital F is defined, let capital F equal to little f of xy minor z. That was my Chinese professor. Minor. Minus z. I shouldn't talk like that. This is being recorded. I get some thumbs down, but sorry. Okay. Yes, sir. That's it right there. Okay. So here this is z is equal to f of x, y. And so basically the capital F, again, is you subtract the z from f of xy. Capital F is f of xy minus z. That's the x squared minus y squared minus z. Now you put the partials, for those partials, you evaluate these partials at the point 325. So this is 2 times 3, you get 6. Capital F sub y at the point 325 is equal to negative 2 times 2, negative 4. And then this guy is fixed always at negative 1. So for part A, you have 6 times x minus 3 minus the 4 times y minus 2 minus 1 times z minus 5 is equal to 0. We get 6x minus 18 minus 4y plus 8 minus z plus 5 is equal to 0. 6x minus 4y minus z. We get minus 10 plus 5. We get minus 5. We get positive 5 on that side. And then part B, just take x minus 3 divided by 6 equal to y minus 2 divided by negative 4 is equal to z minus 5 divided by negative 1. So for a problem like this, where the function is given a little bit different, you go back to that previous problem, see how this function is defined? It looks like that. This previous problem, it was x, y, and z all on the same side. So you just go directly and you compute those partial derivatives. But this is not truly capital F. Capital F says that it has to equal to 0. Right? So capital F of x, y, z to be true is x squared plus 2 y squared plus z squared minus 7 is equal to 0. But it didn't have a z over there, so I didn't even deal with it. Any questions there? Now, to be honest with you, in this section, I'm only going to give you one problem like that on the test, and I'm going to ask that same question. Part A, find the tangent equation of the line. Part B, find the symmetric equation of the line. And the problem will either look like this problem or that next problem. So I can't get no better than that right there. Okay. So if you got that, then we're good. Let's take a 5-minute break. sir. Z minus 2. Yes, sir.